Imagine you run a company that manufactures boxes. If you had a particular volume in mind, you'd likely want to minimize the materials needed for the surface area so that your costs can be lower. If you wanted to build a garden using a specific amount of fencing, you'd likely want to maximize the area of that garden for optimal planting space. This section is going to cover maxima and minimum. Maximum and minimum values can be an important characteristic of a function. Spotting maximums and minimums on a graph is relatively easy, but how could we find these values symbolically? First, we need to set something straight. There are two different types of maximum and minimums, absolute and local. You can see on the graph the absolute maximum is the largest value the function takes on. Conversely, the absolute minimum is the smallest value the function takes on. We will discuss absolute maximum and minimum values once we get to optimization. So for now, let's focus on local maximums and minimums. Let's define these more formally. Local maximum and minimum. The number f of c is a local maximum of f if there exists an open interval I containing c such that f of c is greater than or equal to f of x for all x and I. So for example, if I was looking at the graph on the right-hand side, I can see that right here, I'm going to end up having a local maximum. If I draw a little neighborhood around it, all of the values to the left and to the right of this point are below it. So this is the highest y value. So what a local max and minimum are the y values of the function because it's how high or how low that function is. So in this case, we would say that there's a local maximum of 15. Again, you say the y value because it's that 15, it's that y value, how high up it is, that makes that a local max. And that occurs at x equals 1. Another way that you can write that is f of 1 equals 15 is that local max. For a local minimum, the number f of c is a local minimum of f if there exists an open interval I containing c such that f of c is less than or equal to f of x for all x and I. So again, if we're looking at this graph, if I draw a little neighborhood around right here where y is 10 and x is 0, this would be considered a local minimum because all the values on the left and the right side of it, and that's the big key thing for local mins and maxes, is you have to have values on either side, so there can't be the endpoints of a function. So this would be considered a local minimum. So again, we could say you have a local minimum of 10, so the local minimum is 10. It occurs at x equals 0. Or you could write f of 0 equals 10. But again, that local minimum is 10 because again, it's that y value. We have another local minimum right here, and that occurs at 3, and it is about, looks like 17. Let's look at another example. State the local maxima and minima for the function. So if I was looking at a local maximum and minimum here, again, we could not include, even if this was a closed endpoint, we couldn't include that. Like here, we can't include this for local minimums and maximums because we have to have an open interval for both of them that we're looking at. So we need to be able to look at values on both the left and the right-hand side. So I can look here and see that this point is a local minimum because on either side of it, those y values are above this y value of 2. So we have a local minimum that occurs, so the local minimum is 2. It occurs at x equals 2. So both of them are 2. So the local minimum of 2. There's also a local minimum right here at 4 because again, the values on either side are above it. So we'd also say there's a local minimum at, not at x equals 4, occurs at x equals 4, but that local minimum is 1. And again, I can't count this endpoint because there's not values on the other side. If I look here, this is right at this point, this is a local maximum because all of the values to the left and right of it are below it. So that local maximum is 4. And then it looks like we have another local maximum right here. And that occurs at y equals 3, because again, it's that vertical. So there's also a local maximum at 3, or of 3. So again, those local maximums and minimums, when you're stating them, you're stating the y value. Where it occurs is the x value, but the y value is what those values are. Now let's talk about what a critical number is. In these graphical examples, hopefully you're able to notice that the derivative of a local maximum or minimum is typically 0 or undefined. So notice that here, this derivative would be undefined at that x value, would also be undefined here. The derivative at these two local maximums would be 0. So we can actually formalize this a little bit more in this theorem. A critical number of a function f is a number c in the domain such that either f prime of c equals 0 or f prime of c does not exist. So a critical number is going to be helpful in helping us find these local minimums and local maximums. So if f has a local maximum or minima that at c, so at the x value c, then we'll say that c is a critical number. So again, if you go back to that first graph and then looking at the second graph, which I have on the screen, those local maximum and minimums happen when the function was undefined, and then also when the function had a derivative of 0. So let's look at an example of finding critical numbers. Find the critical numbers of f of x equals x cubed plus 6x squared minus 15. So we define critical numbers as the values where the function either equals 0, the first derivative either equals 0, or the first derivative is undefined. So the first thing that we need to do is find that first derivative. So the first derivative of f is 3x squared plus 12x minus 15. So this derivative is always going to be defined on all real numbers, so we don't need to worry about where it's going to be undefined. But now what we need to do is figure out where is this derivative going to equal 0. So this is going to equal 0 when 3x squared plus 12x minus 15 equals 0. So let's factor this out. I can factor a 3 out of each term and get 3 times the quantity x squared plus 4x minus 5, and then we can continue factoring this further into 3 times the quantity x plus 5 times the quantity x minus 1. So this means that this is going to equal 0 when x plus 5 equals 0 or x minus 1 equals 0. So at x equals -5 or at x equals 1. So this means the critical numbers of f of x are x equals -5 and x equals 1. Let's look at another example. Find the critical numbers of f of x equals x minus 2 times the sine of x on the interval from 0 to 2 pi, including both 0 and 2 pi. So again, let's first find the derivative. So that derivative, the derivative of x is 1, and the derivative of 2 sine x is 2 cosine x. So the cosine function is always defined on all real numbers, so this derivative will never be undefined. So we need to figure out where this is going to equal 0. So it's going to equal 0 when 0 equals 1 minus 2 times the cosine of x. Solving for the cosine of x, first subtract 1 from both sides, and then we'll divide both sides by -2 to isolate the cosine. So we get the cosine of x equals 1/2. So that means what values, when you take the cosine of it, give you 1/2. If you think about that unit circle, cosine is the x values, so it's going to be positive in the first and in the fourth quadrant. And so that value, those special angles, is cosine of pi over 3 gives you 1/2. So that over here would be like to figure out what this angle value is. So it's going to be pi over 3 here. So this would be like taking 2 pi and subtracting pi over 3 to find that other angle value. And if you need a refresher on angles, please feel free to reach out. We have lots of videos in the trig playlist that can help out with that. So that would be 5 pi over 3. So this means that this function will equal 0, the derivative will equal 0 when x is pi over 3, or when x is 5 pi over 3. All right, let's look at another one. Find the critical numbers of f of x equals x squared times the ln of x. So to find the derivative of this, we're going to have to do the chain rule. So this is going to be the first function times the derivative of the second, plus the second times the derivative of the first. So that ends up simplifying to x plus 2x ln of x. Okay, so we know that this is going to end up being undefined. You cannot take the natural log of a number that is less than 0. So we know that no matter what this has to be, these x values have to be, greater than 0. All right, so let's look at where this is going to equal 0. So this function is going to equal 0 when 0 equals x plus 2x times the natural log of x, subtracting x from both sides, or actually let's factor the x out. I'm going to get x times 1 plus 2 times the natural log of x. So setting these both equal, we get that x equals 0, or 0 equals 1 plus 2 times the natural log of x. So negative 1 equals 2 times the natural log of x. Negative 1/2 equals the natural log of x. So to convert this, or to solve for x, we'll convert this into exponential form. So remember, the natural log is the same thing as log base e. So to convert it, be e to the negative 1/2 power equals x. And there you go. So we have that our critical numbers are going to occur in this, and I can, if I wanted to not have negative exponents, I could write it like that, and then I could even write it even. Anything to the 1/2 power is the same thing as the square root. All right, so if I'm looking at these, this is not in the domain of this derivative because, and the original function as well. With these, both the original function and the derivative function, our x values have to be greater than 0. So that means there's only one place that this derivative is going to end up equaling 0, and that's going to be at 1 over the square root of e. So that is our critical number. All right, now let's look at finding the critical numbers of the function h of x equals arc times the sine of x. So the derivative of the arc sine, sorry, not arc times the sine of x, of the arc sine of x. So the arc sine of x, the derivative of that, remember arc sine is the same thing as sine inverse. So that's 1 over the square root of 1 minus x squared. So in looking at this function will never equal 0. The only way it can equal 0 is if I have 0 in that numerator. The numerator is always going to be 1. But this function will be undefined when that denominator equals 0 because you cannot divide by 0. So we know that h prime of x is never going to equal 0, but it is going to be undefined when, I'm going to just write this out. So undefined when the square root of 1 minus x squared equals 0. Again, because we can't divide by 0. So to solve for x, the first thing that we do is square both sides. So we'll be left with 1 minus x squared equals 0 squared, which is 0. Let's move that x squared over to the right-hand side. and then we'll square root. And don't forget, when you square root, it's always plus or minus. So we would say that there are critical numbers for this function at both +1 and at -1.